Today we're going to cover Chapter 7, Section 1, and we're going to deal with angles of polygons. So first we have to, as always in geometry, we seem to need to recognize vocabulary words. We have to understand them and be able to identify the parts. So each segment that forms a polygon is a side of the polygon. So in other words, segment AE and AB and BC, CD, and ED all form this outer polygon, right? You have these outer sides and it forms this five-sided figure. Well, each of those segments is considered a side and each of those segments meets at a common endpoint. For example, EA and AB meet at A. AB and BC meet here at B. And notice that we have these endpoints. Well, each one of those endpoints is called a vertex. And so then you're going to see that you have this thing called a diagonal in here. And basically, if you have a segment that connects two non-consecutive vertices, it's called a diagonal. So in other words, for example, B and D are not consecutive points. A and B are consecutive points, or vertices. B and C are consecutive. A and E, E and D, all these outer ones are consecutive. But then you're going to notice that B also connects to D right here through the middle, and it kind of bypasses C. Well, those segments that bypass vertices, they're basically non-consecutive. We call those diagonals. And every shape will have some kind of diagonal. If it has three or four or more sides, it's going to have a diagonal. Another example of a diagonal here would be, for example, from A to D. We've got B to D. We even have E to B and E to C. So there's lots of diagonals that can be drawn within. Obviously, the diagonals go into the actual shape. So once we know how many sides we have, we can name our polygons. Now, we did this in a previous chapter when we discussed polygons. Remember, polygons are two-dimensional, which are flat, closed shapes made up of line segments. And so we learned back in another chapter that if it has three sides, it's called a triangle. If it has four sides, it's a quadrilateral. Notice the roots there, prefixes, roots, I'm not sure, but 5, penta means 5. 6 is represented by hexagon. 7 is a heptagon, and I have also seen it called a septagon. So just kind of remember that. Hepta or septa means 7. Octa means 8. Nona means 9. Deca means 10. A dodeca is 12. And so these are the ones I would want you to name, because in word problems I might say it's a hectagon or a heptagon or a dodecagon, and I need you to know that it has the number of sides. Anything other than what's on this chart, we'll call it an n-gon. So a 13-sided figure, we'll refer to it as a 13-gon. Okay? A 20-sided figure is a 20-gon. Okay? And that's how we'll refer to it. So these are the most common ones, but you do need to know, if I ask you for the name of a 12-sided figure, I need to see you write dodecagon, not 12-gon. Okay? So if it's in this chart, you need to memorize. So memorize these. Okay? Anything else, you can use the n-gon. Okay? So remember when we learned that the sum of the interior angle measures of a triangle, remember, of a triangle is 180 degrees. Well, if you can draw all the possible diagrams from one, or diagonals from one particular vertex, you can create a bunch of triangles. Remember that the sum of the angles of the triangles is going to be 180 for each triangle. So if there's 3 triangles, it'll be 3 times 180. So for example, here you have one triangle, so the sum of the interior angles is 180 degrees. In a quadrilateral, if I pick this vertices, then notice that I have 280 degree triangles, which means this is equal to 360 degrees total. Now, what we're talking about when we're talking about 360 is the sum of angle 1, angle 2, angle 3, and angle 4. Okay? So here, notice we have a 5-sided figure, a pentagon. Well, again, if I pick this vertices and I connect all my diagonals to it, notice that this would be 180, this would be 180, this would be 180, and all together, the sum of the interior angles would be 540 degrees, and so on and so forth. So again, if I have a hexagon, I can turn it into 4 triangles, so it's 180 times 4, or 720 degrees. So you might say, well, this is great, but if I have a dodecagon, which has 12 sides, am I supposed to make a bunch of triangles and figure out how many there are? Well, not really. There's a formula that's going to help this out a little bit. So they start out by showing you the pattern. If you have a 3-sided figure, you can create 1 triangle, and 180 times 1 is 180. If you have a 4-sided figure, you could create 2 triangles, and 180 times 2 is 360. If you have a 5-sided figure, you can end up creating 3 triangles, and you get to 180 degrees. If you have a 6-sided, like the hexagon we did in the last page, you can create 4 triangles, and 4 times 180 is 720. And if you notice, the pattern is, no matter what the number of sides is, the number of triangles is always the number of sides minus 2. So if I multiply the number of sides minus 2 times 180, I'm going to get my interior angles. So here is the theorem that tells you that. So after somebody figured this pattern out, a theorem was proven over and over and over again, so it was created. It says the sum of the measures of the interior angles of a convex n-gon is n minus 2 times 180. So if I have a 10-sided figure, right, or let me give you the correct name, if I have a decagon, I know the number of sides is 10, and so I know the interior angles sum is going to equal 10 minus 2 times 180, or 8 times 180, which is equal to, I think, 1440 degrees. And so, again, remember, a corollary is something that stems from a theorem, and so that it's kind of so obvious it follows it. And so the corollary basically says that the sum of the measures of the interior angles of a quadrilateral, that means n is 4, is 360 degrees. So instead of letting you having to figure out this, it basically tells you exactly what the degree measure is without you having to use the formula. So now we're going to talk about some terms that we use with triangles, but we want you to understand that those terms work with polygons. Remember, in a triangle, an equilateral triangle was a triangle that had all sides were congruent. So in a triangle, you get that. Those little tick marks show you congruency. In a quadrilateral, you get that. In a 5-sided figure, you get something that might look like that, and so on and so forth. Equiangular means that all the angles are congruent. So in other words, in those same shapes, if they were equiangular, these 3 angles in blue would be the same, or these 4 angles in blue would be the same, or these 5 angles in the pentagon would be the same. Okay? And so if we happen to have both a equilateral shape or polygon and a equiangular, we have a shape that's called regular. And a regular shape is when we have a shape that has all sides and angles are congruent. Okay? So when you think of a shape, most of the time what comes to your mind is a regular shape. When you think back to like the little shape sorter toys that you probably had, or a little sibling had, or a little cousin, you recognize that when you had to insert the triangle, that was the triangle that you usually had. You didn't often have a right triangle or an obtuse triangle. You had this equilateral, equiangular triangle. When you had a quadrilateral, you probably had a square, because again, that's equilateral, equiangular. They probably didn't give you a rectangle. When you had a pentagon, you probably had a traditional pentagon that looks like this, or like the Pentagon in the United States. It has that shape. And so again, a regular shape is what probably comes to your mind when you think of things. But again, in geometry, you have to be prepared also for non-regular shapes. You know, you can have a quadrilateral, that's a square, which is great. Again, equilateral, equiangular. Or you can have a quadrilateral that looks like this, you know, 2, 3, and 4. And that's also a quadrilateral, but it's probably not what came into your mind when you thought of a four-sided figure. So first we're going to get questions where I'm going to ask you to classify a polygon by the number of sides. Then I'm going to ask you to tell me if it's equilateral, equiangular, or if it happens to be both, then it's irregular, and then explain. So when I look at this, I'm going to look at this picture, and I'm going to first determine how many sides it has. 1, 2, 3, 4, 5, 6. Counting is not a bad thing. So if n is 6, I know that I have a hexagon. Now, what kind of hexagon do I have? A regular one, or one that has different angles or different sides, or both? Well, when I look at the sides, notice I see the same single tick mark for all 6 sides. That means it's equilateral, okay, because all 6 sides are equal. And then look at the interior angles. Notice that all of them have a single mark. That means that all these interior angles are the same. And so it's equiangular. And you know, we already talked about when it's equilateral and equiangular, then it's regular. So this is a regular hexagon. When I go to the next shape, I do the same thing. I start, number 1, how many sides does it have? It has 4 sides. So n is 4, which means the correct name is a quadrilateral. Okay. Now when I go to my sides, I notice that the left and right side are equal, but the top and the bottom side are not equal to the left and right, even though they're equal to each other. So I know that this is not equilateral. And notice the same goes for my angles. I have a single tick mark, so these 2 angles are equal, but then I have doubles, which means these 2 are equal. But all 4 are not equal with each other, so it's not equiangular, which means it's also not regular. It's just a plain old quadrilateral. And the last shape is really tricky. The last shape, we need to look at it, and first we need to figure out the number of sides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if n is 12, I know this is a dodecagon. Okay, so a dodecagon. That's the easy part. And I also see that all the sides have a single tick mark. And so there are 12 congruent sides. So it is equilateral. Okay? The issue here is going to come into equiangular. And they make it look at first that it is. Notice they loaded up with right triangles. Or not right triangles, right angles. And if you go through the interior angles, you're going to see that you have 8 angles in here that are equal to each other. They're all right angles. But notice these ones here. These 4, they try to make you think that those are the other 4 equal angles, but those are exterior angles, okay? Or they're on the exterior side. So they're not interior angles, okay? Those aren't actually exterior angles as well, but they are not on the interior of this shape. So what angles are on the interior? Well, this really big, almost full circle angle is the interior. And those 4 green angles are not congruent to all the right angles inside that we found. And so this one is not equiangular. So because it's not equiangular, it's not regular. It's just an equilateral dodecagon. So you can have one that has no equal sides or no equal angles. You can have one that has just equal sides, and you can have one that is both, which ends up being regular. Now, we mentioned exterior angles in the last slide, and so I want to be sure and clear that we know what an exterior angle is. So I'm going to start out by drawing the original shape. This started out as a 5-sided figure here in blue. This is a pentagon. And what they did was they took the sides, one side here, and they extended it out and created this exterior angle. And if I go to every side and extend it, I'm going to be creating a different angle every time. I'm going to do the tick marks that match the number. So extend the side, and now I have angle 4. Extend the side, and now I have exterior angle 5. And over here, extend it, and this was the original exterior angle. But notice, if you have a 5-sided figure, okay, you're going to have 5 interior angles, and you're going to have 5 exterior angles for everything. So what you can say is, depending on the number of sides, n sides, you're going to have n interior angles and n exterior angles, okay? So what do the exterior angles add up to? Do they also have a formula? Well, we're lucky because they don't have a formula. They always add up to 360 degrees, no matter how many sides. No matter how many sides the polygon has, okay? So you don't have to worry like in the interior angles where you need to know the formula, okay? This is always 360. So if it's a dodecagon, guess what? The exterior angles add up to 360. If it's a pentagon like this one, the exterior angles add up to 360. So now this is where it gets really interesting. And this, notice, this is a different formula than what we had. Obviously up here, this is the sum of the interior angles. Okay, this is just the sum of the interior angles. Down here, this is the number of number of sides. Okay, so this is a special formula to find the measure of each individual interior angle if it's a regular polygon. You see, if it's regular, all the angles are the same, and so we can use an average of the sum to find that out. So for example, we already know that a regular triangle, right? We learned this before. We know that each interior angle is 60. Remember, it was 60, 60, 60. And I think you guys remember because you said, well, if they add up to 180, 180 divided by 3 is 60. Well, let's apply the formula and show how the formula would get you this as well. Remember, the formula is n minus 2 times 180. That's going to give me the sum of all 3 of them. And then if I divide by 3, or let me just divide by n, right? If I divide by n, it's going to give me each individual angle. Well, let's apply it. 3 minus 2 times 180 over 3. Notice that's 1 times 180 divided by 3, and it's 60 degrees. So this is obviously if n is 3. So if I have a shape like a square, remember a square, all the 4 angles inside add up to 90. You kind of know that. But again, let's do it mathematically. If n is 4, then 4 minus 2 times 180 divided by 4 should give me the value of each interior angle. So 360 divided by 4, and it equals 90, and it does. So again, this is the formula. You already knew it for a triangle, and you already knew it for a square. However, it's good to know the formula because now you know how to find the measure of each interior angle of a regular pentagon, decagon, octagon, 13gon, whatever I give you, you can figure out. So it says here, find the sum of the interior angles of these polygons and then find the sum of the exterior angles. Well, here's A and here's B, here's A and here's B. B is the exterior angles. Guess what? It doesn't matter to me how many sides my shape has, okay? B is always 360 degrees. B's easy, okay? The interior angles is where the math is involved. So if it's a heptagon, n is 7, so my formula is n minus 2 times 180. So 7 minus 2 times 180, or 4 times 180, which is going to be 900 degrees. If I go to 17, or not the 17 gone, again, no big deal. And I write the formula every time so I can commit it to memory. You should do the same. 17 minus 2 times 180, or 15 times 180. And I don't know the answer to that, so 40. And it should be 2700 degrees. Now remember, you can start using a calculator in the class. So at home, you should practice doing the math on your own and double check it with a calculator. On a test, you can use the calculator. Okay? And so again, that's how we find the sum of the measures of the interior and the exterior. Now, this is all the interiors. This is the sum of all 7 interiors. Now, how much is each interior angle? Well, we're not sure. If it was a regular polygon, a regular heptagon, I would divide 900 by 7 and I'd get each one. But if it's not regular, they could all be different. They just have to all add up to 900. So looking for the word regular is pretty important. So here it says, find the number of sides of a convex polygon with the sum of the measure of the interior angles equal to 900. And they want the number of sides. So they're looking for n, okay? So again, remember the formula. The sum of the measure of the interior angles is n minus 2 times 180 equals the total sum, right? Okay, well, notice that they gave us the sum. So I'm plugging 900 in here, and I need to solve for n. Now I just did that on the last slide, and n is 7. But again, I'm not supposed to know that yet, right? So I can do the math 2 ways. I can distribute the 180. I get 180n minus 360 equals 900. I could add 360 to both sides. I get 180n equals 1260. And if I divide both sides by 180, I'm going to get that n equals 7. Let me make sure that that's true, right? 180 times 7, 0, 56, carry the 5, 1260. Yep, it works, right? Okay, now that was one way. I could have made my math a little simpler, or maybe, I don't even know if it would have made it simpler. But when I got to here, I could have just divided the left side by 180 and not ever distributed the 180. That would have left me with n minus 2, and 900 divided by 180 is 5. And then I would have added 2 to both sides, and I would have found again that n is a 7-sided figure. So n is 7. And then lastly, the slide says, find the measure of each interior angle and each exterior angle of the given polygon. So again, let's think about that. A regular quadrilateral, sort of already did that one, right? But it's regular. So I know that I'm going to do interior here. Let me do each interior angle, and I'm going to do each exterior angle. The formula for each interior is n minus 2 times 180 divided by n. So in this case, I'm going to have, remember, n is 4. So I'm going to do 4 minus 2 times 180 divided by 4. And I did this one for you already. 2 times 180 divided by 4, 360 divided by 4, and my answer is 90. So each exterior is 90 degrees. I'll try to do it a little neater. Now, each interior angle, sorry. Now, each exterior angle, remember the sum is always 360. So all I have to do is divide 360 by 4, and I'm going to get 90 degrees. So there's my exterior. So let's do the regular octagon. Again, an octagon, n is 8. So I'm going to come over to here, and I know that I'm going to do 8 minus 2 times 180 all over 8. So 6 times 180 all over 8. 6 times 180 is 0. 1080 divided by 8. And I'm going to get 1, 3, 135. So each interior angle is 135 degrees. And when I come over here, again, it's easy. It's 360 divided by 8. And that's going to be 45 degrees. So my interiors are here on the left. My exteriors are on the right. And again, a regular 15 gon. So the sum is 15 minus 2 times 180. And then I divide it by 15 sides. So I'm going to get 13 times 180 divided by 15. 13 times 180 is going to be, it's 1800 plus 540. So it's 2340 divided by 15. And when I do that division, I'm going to get 1, then I'm going to have 84, which is going to be 575, and then 90, which is going to be 6. So it's 156 degrees. So that's the sum of each individual interior angle. And then the exteriors, again, is just 360 divided by 15, and that's going to be 24. And so I would like you to notice before we move on and end this, because this is the last slide, I would like you to see a pattern. Notice the interior angle and the exterior angle here have a sum of 180. Notice interior plus exterior, sum of 180. Interior plus exterior, sum of 180. That's not a coincidence. The interior and the exterior angle form a linear pair, and so they're supplementary, which means they add up to 180. So again, let's kind of think about that. Notice if I have a triangle here, and I know my interiors are 60, 60, and 60, if I extend this out, I know this piece here is 120, and 60 and 120 equals 180 degrees. If I have that regular square where I know this is 90 degrees, if I extend this out, I know this piece is also 90 degrees. So interior and exterior are both 90. If I have that pentagon that we show, or even an octagon, right? Here's a regular octagon, looks kind of something like this. And I know that this angle right here is 135 degrees. If I come over to here and I extend this, I know this little piece here, notice they form a linear pair, and I notice that this little piece is 45. And so again, that's kind of how we know it's always that way. And it's not just in regular shapes, okay? I can have any kind of triangle. I can have this, I can have a 90, a 40, no, I don't want to give you that one. I can do a 90, a 50, and this is 40. And if I extend this, I know this side here is 140. So the fact that they form a linear pair is all interior and exterior angles. So they always add up to 180, and it's a great way of checking yourself. But since we're only talking about regular shapes here, those are the ones I want to highlight.